Hey guys, how's everyone doing? Make sure you've got your lesson book ready for lesson 2. And anytime you have any questions while I'm going through this video, just post them in the chat here and I'll do my best to keep looking over and answer your questions as I go. So we're going to do lesson 2, which is on vector addition. And I hope yesterday's lesson went well on intro to vectors. So just a quick summary of that. In order to do this lesson, you have to be familiar with what a vector is, right? So a vector is basically something that has magnitude and direction, and it can be represented with a line segment with an arrow. And this vector has two components. It has the tail, which we label with a letter, and a tip, which we label with a letter. So this vector is going from A to B, and the notation we use to represent that vector is AB with a vector symbol above it, right? This indicates that we have a vector that goes from A to B. All right, so let's get started with lesson 2, where we're going to add two vectors together. So in your lesson book, we'll go through this together and fill out the blanks as we go. When you add two or more vectors, you are finding a single vector called the resultant vector. So anytime you are adding vectors, the sum is called the resultant of the vectors. That has the same effect as the original vectors applied one after the other. And there's two ways that we can add vectors to get a resultant vector. I'm going to focus on this method here, the tip to tail method. There's another method which does essentially the same thing called the parallelogram method. But I'm going to focus on tip to tail method because that's the method that I'm going to be using anytime I add vectors. So if we have two vectors, so let me just show you two vectors here. So we've got vector A and vector B. So vector A has a very specific magnitude and direction, so does vector B. Let me see if I can find, there we go, vector B. And if I wanted to add these two vectors, here, I'll do this down below actually. If I wanted to add two vectors, so let me get vector A. Here's vector A, and let me get vector B. If I'm given these two vectors and I want to add them together, what you have to do is you have to place them tip to tail. So I'll call this one vector A, and this one was vector B. So if the vectors are given to you here in this orientation on your page, if we want to add those two vectors together, you have to first start by positioning the two vectors tip to tail. So you put the tail of vector B at the tip of vector A, and then the resultant of those two vectors is the vector that goes from the tail of the first vector to the tip of the second vector. So we would say that that is vector A plus B. So when you are repositioning the vectors so that they're tip to tail, make sure that you're not changing their direction or their magnitude at all. You're just changing the position on the page. So that's called the tip to tail method. So it says the sum of vectors A and B can be found by translating the tail of vector B to the tip of vector A. And the resultant is the vector from the tail of A to the tip of B. So place them tip to tail, right? Here the vectors are tip to tail, and the resultant goes from the tail of the first vector to the tip of the second vector. And this is just a note here. What if we add opposite vectors? So if we have two complete opposite vectors, right? So I have vector BA and I have vector AB. If I were to take vector AB, which is represented by that vector right there, and place it tip to tail with BA, let me see if I can do that. Notice if I were to try and draw a vector from the tail of AB to the tip of BA, well, that's right here. It's just like a point. There's no vector that goes between them, so we call that the zero vector. So if you're adding opposite vectors, what you get, you don't get zero, you get what's called the zero vector. So you write 0 with the vector symbol above it. And remember, opposite vectors are vectors that have exact opposite directions and have the exact same magnitude. Make sure you guys are letting me know if you have any questions in the chat about any of this as we go. Okay, the last thing I need to go over with you before we do any actual examples is how do we subtract two vectors. So I went over with you how to add two vectors, right? We placed the vectors tip to tail, like in this diagram here for adding A and B, place them so that they are tip to tail, and then our resultant goes from tail of first to tip of second. How do we subtract two vectors? Well, there's a couple options. The first option, which probably will make the most sense to you, is called adding opposites. So let's say we want to do vector A minus B. Well, we could think of that as A plus negative B, right? Adding a negative is the same as subtracting. And negative B would have the exact same magnitude as B, just be in the opposite direction. So in this case, if we have vector A and B, so let me just draw those below again. So here's vector A, and vector B is this one here. Let me move them so they're below. If I asked you to find A minus B, so here's A, and here's vector B. If I asked you to find A minus B, there's a couple options. Option number one would be to add the negative. So what we do is we take this vector and reverse its direction. So now it becomes negative B. So now this is vector negative B. And now we just add these two vectors together. So we place them tip to tail, like so. And the resultant goes from the tail of the first vector to the tip of the second vector. So it would look like that. And that's indicated in this diagram here. That's what A minus B would look like. The other method to add vectors is to, instead of placing them tip to tail, you can just leave vector A and B as they are, so you don't have to make either of them negative. And instead of placing them tip to tail, you place them tail to tail. But then where the resultant goes is different. So instead of placing them tip to tail, leave vector B as it was originally, and place the two vectors tail to tail. And then the difference of the two vectors is going to be the vector that goes from the tail of B to the tip of A, and that would give you A minus B. So it would look like this. And notice that this resultant right here is the same as this resultant. They're in different positions on the page, but they have the same magnitude and direction. So it doesn't matter which of these two methods you do. You can either add the opposite or place them tail to tail and then get your resultant that way by placing the resultant from the tail of the vector you're from the tip of the vector you're subtracting to the tip of the first vector. Right? If you're doing A minus B, it goes from tip of B to tip of A. If we were doing B minus A, it would be going the other direction. So that's all of the rules for adding and subtracting vectors. Let's actually try a couple examples so you can see how we actually do these problems. So here are three vectors, A, B, and C. Suppose you're given the vectors A, B, and C in the diagram here. Use these three vectors to sketch what A minus B plus C looks like. So you're going to need some type of ruler or be good at estimating when you're drawing, because when we reposition these vectors to get the resultant of A minus B plus C, you're going to need to make sure you're not changing the direction or the magnitude of these vectors at all. So if I want to do vector A minus vector B plus vector C, another way of thinking of that would be doing vector A plus negative vector B plus vector C. Right? That adding a negative is the same as subtracting. So let's attempt this. And when we're adding vectors, so we're going to add three vectors together, we have to make sure we place them all tip to tail. So let's take vector A, and let me just position it here. And then I'm going to have to add negative vector B. So negative vector B would be the exact same magnitude as B, but be in the opposite direction. So I have to reverse its direction. So I reversed the direction of B, so now this is negative B. And now if I'm adding it to A, I have to place it tip to tail with A. So place the tail of negative B at the tip of vector A. And now I have to add vector C. So what I do is I take vector C and place that tip to tail with negative vector B. And then my resultant of these three goes from the tail of where I started to the tip of where I finished. And you can always do that when you're adding vectors. Place all the vectors that you're adding tip to tail, and then the resultant goes from where you started to where you finished. So let me draw that resultant vector. And I'll do this one in red. So the resultant vector looks like this. So we could label it with our a minus b plus c. So that red vector is vector a minus vector b plus vector c. Any questions so far, guys? Are you understanding how we add vectors by placing them tip to tail? And you're going to have some type of ruler handy, so when we're repositioning these vectors, you can try and draw them as accurately as possible. Ready for another example? Okay, I'll keep checking back in the chat if you guys have any questions. So how would we add them if they had values? So we still position them the same way, but if we were actually trying to calculate the actual magnitude of the resultant, we'll do that later. We'll have to use some trigonometry. So we'll have to use our sine law, cosine law, SOHCAHTOA, and that kind of stuff if we wanted to actually figure out what the magnitude of this was, if we knew the magnitudes of A, B, and C. All right, let's try example 2. So here's a rectangular box, so you have to know some properties of rectangular prisms for this, right? So you have to know that like side OA and side CB are going to be parallel and equal in length, and so on. So in this diagram, I've named 3 of the vectors. So this vector from O to A, I've named vector A. From O to C, I've named vector B. And from O to D, I've named vector C. It says express each of the following vectors in terms of those 3 vectors. So we want to come up with an expression for vector BC. So let me just draw vector BC for you. So going from B to C, we want to come up with an expression for that vector using only vectors A, B, and C. So notice that vector BC has the exact same magnitude as vector OA, but it's going in the opposite direction. And vector OA is equal, we named it vector A, so vector BC, since it's the exact same magnitude but opposite direction as vector A, we say that it is equal to the negative of vector A. Negative vector A. Let's try part B, vector GF. So vector GF is up here. Notice that that vector has the exact same direction and magnitude as vector A, so this one is just equal to vector A. How about vector OB? So vector OB, now we're going to have to start adding some vectors here. So vector OB, notice that to get vector OB, I can express it as a sum or difference of other vectors, and I can express it as a sum of vectors that are placed tip to tail together. So let me draw a couple vectors placed tip to tail, and you'll see what I mean. So to get this vector here, I could add this vector and this vector. Those vectors are placed tip to tail, so the resultant of those two added together would be from the tail of where I started to the tip of where I finished. So this vector OB could be expressed as a sum of this vector, which is vector A, and this vector over here, which is equivalent to vector B. So I can say vector OB is equal to vector A plus vector B. Oh, let me move my diagram a little bit here. You guys couldn't see what I did there. Let me just move this. Can you see that now? So what I did to get this one, vector OB, I added vector A and vector B. So those two added together equal the vector from the tail of A to the tip of vector B there. All right, let's try part C. Let me just get rid of all this stuff. Okay, so part C asks us to find, oops. Let me just reposition all of this for you now that you can see the actual box that we're working with. Okay, let's try, part D, vector AC. So we want vector AC, so the vector going from A to C. If we want that vector, we can express it as a sum of vectors that are placed tip to tail with each other. So let me place a couple of vectors tip to tail with each other that will get me from A to C. So I could go here and then there. So those two vectors are placed tip to tail with each other. And those two vectors, I need an expression equivalent to those two vectors. Well, this vector that I drew going from A to O is the opposite of what vector A was. So I can call that vector negative A. So let me just do this in a different color. So I need to go here, which is the opposite of vector A, so that's negative A. And then I went here, which is vector B. So vector AC is equal to negative A, so negative vector A plus vector B. Or you could write it as vector B minus vector A. That's equivalent. So Joe, what do you mean by what direction the lines are going? So like vector BG, for example, I know it starts at B and finishes at G. So when I draw vector BG, I know I have to start here at B and finish up here at G. So that's why the arrow is pointing towards G. So like in the notation, the first letter tells you the tail, the second letter tells you the tip. And now I need to, when I'm trying to figure out an expression for this vector, for vector BG, I have to place some vectors tip to tail to each other to get from B to G. So I need to go from, and there's multiple ways to do this, but I need to go from B to F, and then I need to go from F to G. That's one possible way that we could add some vectors to get from B to G. And notice that this vector is going from B to F. And actually this one we don't have oh yeah, we do have an expression for it. C. It's vector C. It's going in the exact same direction as vector C. So this vector over here I could call vector C, right? It's the exact same magnitude and direction as that vector. So this is equivalent to vector C. And then this vector is going in the opposite direction of what vector A was going in, right? Indicated by the arrowhead on vector A is going that way. And vector FG is going in the exact opposite direction, but it has the same length. So we call this equal to negative of vector A. And then so to get from B to G, if I place these vectors tip to tail, it means they're being added together. So vector C plus negative vector A equals vector BG. So this equals vector C plus negative vector A, which we could simplify to just be vector C minus vector A. All right, vector OF. So let me just get rid of all this stuff again. Let's do our last one here. Vector OF. So that means it starts at O and it finishes at F. So we're going to have to come up with a sum of vectors placed tip to tail that start us here and finish us here. So there's multiple ways to do this, but I'll just draw the first sum that comes to my mind. So I could go in this direction. I could go from O to A, I could then go from A to B, and I could then go from B to F. And then I just have to come up with an expression for those three vectors. So this vector, OA, we were told in the question that that was vector A, so we've got that. Vector AB is the exact same magnitude and direction as OC, which was labeled as vector B, so this is vector B. And BF is same magnitude and direction as OD, so this is equal to vector C. So vector OF is just equal to the sum of those three vectors, right? They're all placed tip to tail, right? Tip to tail, tip to tail. So the sum of those three vectors goes from the tail of where we started to the tip of where we finished. So this is equal to vector A plus vector B plus vector C. So there's going to be lots of these types of diagram questions in your homework and on evaluations. So let me know if you guys have any questions with them before we move on here. So the important thing is that we are coming up with an expression for a vector by adding vectors together, making sure they're placed tip to tail. And the resultant always goes from tail of where you started to tip of where you finished. Okay, I'm going to move on through the lesson then. This table is honestly just showing you that when adding and subtracting vectors, normal algebra rules apply, right? When you're adding vectors, it doesn't matter the order that you add them in. U plus V is the same as V plus U. So when you're adding vectors, it doesn't matter which one you think as your starting vector and which one you think as the one you're adding to it. You'll end up with the same resultant either way. And these properties hold true as well, right? If you're adding three vectors together, it doesn't matter which pair of them you add first. Like you could add U and V together and then add vector W, or you could add vector V and W together and then add vector U. So that doesn't matter either. And if you're adding a zero vector to a vector, it doesn't do anything. That's all that shows. So let's just work with a little bit of algebra with these quickly. So example 3 says simplify each of the following, and this is just like collecting like terms. So this is vector U plus vector V minus vector U. So we can just drop the brackets, and we've got vector U plus vector V minus vector U. Treat these just like terms. Vector U minus vector U. Make sure you don't just like eliminate those and don't write anything. When you have a vector minus itself, you're left with the zero vector. So we'd say vector V plus the zero vector. And part B, we've got vector P plus vector Q minus vector P. And that, whatever that is, we need to subtract vector Q. And notice if I drop the brackets here, just like I would if I were working with normal numbers, vector P minus vector P is the zero vector, and vector Q minus vector Q is the zero vector. So all I'm left with is the zero vector. So don't just write zero, just put the vector symbol above the zero when we do that. And over here, I suppose I could have used this property up here, vector V plus the zero vector. We could just simplify that to just vector V. But if you're left with just the zero vector, you have to include that. But if you're adding the zero vector to something, you can leave it as just that something. But if it's just the zero vector left, write the zero vector. This is just a couple quick properties before we actually get to example 4 and 5 are the important ones I want to talk to you about. Liam, do you not have to write two zero vectors if three are two pairings? No, so I think you're talking about like back here. You're saying would we have had to write like zero vector plus zero vector? No, because zero vector plus zero vector is just a single zero vector. So you only have to write it once, if that makes sense to you. So just a couple quick properties. If two vectors are working in the exact same direction, then the magnitude of the resultant, right? If I place, so vector A and vector B, see they're going in the exact same direction. When they're placed tail to tail, the magnitude of that, so the length of vector A plus B, is equal to just the magnitude of A plus the magnitude of B. And similarly, if they were being subtracted, the magnitude of the resultant of these two, of vector A plus negative vector B, is equal to the magnitude of A minus the magnitude of B. That's pretty straightforward. Like if the magnitude of A was 3 and the magnitude of B was 5, let's just make up numbers here, then you could see the length of this resultant would just be 8, right? Simple. And over here, let's say this was 10 and this was 7, well, the resultant would just be 3. So that's all this is indicating to you, that if they're going the same direction, you can just add the magnitudes and get the magnitude of the resultant. But most often, things are not going to be going in the same direction. So we're going to need to know trigonometry to be able to solve for magnitudes of sides. And here's all of the stuff you should remember about trigonometry from throughout your high school math career. So you should know Pythagorean theorem works for right triangles, no SOHCAHTOA, no sine law, and no cosine law. And we're going to, as much as possible, avoid using sine law to solve for angles. So if you're trying to solve an angle, let's try and use cosine law instead of sine law, because if you remember, there's something called the ambiguous case of sine, where if we use sine to find an angle, we may have to consider that there are two possible options for what the angle could be. So we're going to give preference to cosine law, if possible, to be able to solve for an angle. So let's see a couple questions where we're going to need this trigonometry to be able to solve for a magnitude of a resultant vector. So example 4. Given vectors A and vector B such that the angle between the two vectors is 60 degrees. And when a question says angle between two vectors, that always means if the vectors are placed tail to tail. So I know this seems like a lot of properties to remember right off the bat, right? When adding, they have to be tip to tail. When it gives you the angle between two vectors, they're tail to tail. But after we get through these first few lessons, you'll get used to all of these properties. So the angle between them is 60, and these absolute value signs, that means magnitude. So it just means the length of vector A is 3, and the length of vector B is 2. The question asks us to find just the magnitude of the vector A plus B. It doesn't ask us to find the direction of A plus B, it just wants to know what's the magnitude of A plus B. And that's what those absolute value symbols mean. They mean the magnitude of it. So if I want the magnitude of vector A plus B, the first thing I'm going to have to do is I'm going to have to generate vector A plus B by repositioning vector A and B. Right now they're placed tail to tail because in the question it gave us the angle between them when they're placed tail to tail. When I add vector A and B together, they have to be placed tip to tail. So I have to place the tail of vector B. So I'll just copy and paste vector B so that I keep its exact same direction and magnitude. You'll have to use a ruler to do this. And place it at the tip of vector A. So this is just a copy of vector B. I just positioned it over here. But notice it's the exact same magnitude, exact same direction. And I did that because when adding two vectors, they have to be placed tip to tail. So now I'm going to draw vector A plus B. Vector A plus B would go from the tail of A, where we started, to the tip of B, where we finish. So that's vector A plus B. And I can label that by writing vector A plus vector B. And the question asks us just find the magnitude of this. So if we're going to find the magnitude of this vector, well, let's see what we know about this triangle I have here. So in this triangle, I know the magnitude of this side is 3, and I know the magnitude of this side is 2. The question gave us that, so we know two sides. Let's see if we can figure out an angle in this triangle. So back in, I don't know what grade you learned it in, but there's a bunch of parallel line theorems. And notice here, this line and this line are parallel. So the angles on the interior of it, we call them co-interior angles, add to 180. So the angle inside, the angle here is 60, which means this angle here has to be 120. So let me just write that. So this angle is 120 degrees. And I got that because I knew that this angle and this angle had to add to 180. So now I know a side length, and the angle contained by those two side lengths, and I want the length of the side across from it. So if we look back to that list of rules for trigonometry, we can use the cosine law when you know two sides and a contained angle, and that's exactly what we know. We know two sides and the angle contained by those two sides. So let me rewrite cosine law for you. So cosine law would give us the length of this side squared. So I'd say magnitude of A plus B squared equals the magnitude of this side squared. So magnitude of vector A squared plus magnitude of vector B squared minus 2 times magnitude of A, magnitude of B, cosine of the contained angle. So cosine of 120 degrees. So using cosine law, that's what I could generate for this triangle here. This side squared equals that squared plus that squared minus 2 times cosine of the contained angle. And then we just have to plug in what we know, and we'll get the magnitude of the resultant vector. So 3 squared plus 2 squared minus 2 times 3 times 2 cos 120. So we get 9 plus 4 minus 12 times cos of 120. It has a reference angle of 60, but it's in the sine quadrant, right? 120 is here, reference angle of 60. It's in the sine quadrant, so I could do cos of 60, which is a half, but I have to make it negative. So it'd be negative a half. And what I have here is 13 plus 6, that's 19. So keep in mind, this is what the magnitude of A plus B squared is equal to. So if I actually want the magnitude of A plus B, I have to move that squared over by square rooting. So I get root 19. So the magnitude of A plus B is root 19. So now that we actually had magnitudes of these vectors, now we could actually figure out the magnitude of the resultant vector using the cosine law. And we're going to use cosine law a ton in this chapter, so you'll get super comfortable with this formula. All right, let's move on. We have 2 examples left. Any other questions about that last one while I set up for this one? Okay. This question says an airplane heads due south at a speed of 300 kilometers an hour. So it's going south, so straight down at 300 kilometers an hour. So we know its direction and we know its magnitude. And that's what every vector has, a direction and a magnitude. So it's going down at 300 kilometers an hour. So I know this vector, its magnitude is 300 kilometers an hour. And then it says there's some wind that comes. It comes from the west. So if you think of your compass, west is here, so it's coming from the west, which means it's going that way. And the wind has a velocity of 100 kilometers an hour. So it gives us its direction and its magnitude. So it's coming from the west, and it's meeting the plane, and its magnitude is 100 kilometers an hour. And we are interested in what is the resultant velocity of the airplane. And the resultant, remember that word means the 2 vectors added together. So we need to figure out what vector do we get if we add the plane velocity with the wind velocity. So what do we get if we add those 2 vectors together? So if I'm adding those 2 vectors together, they have to be placed tip to tail. So I'll put the tail of the wind vector at the tip of the airplane's velocity vector. And remember, the order of adding doesn't matter. It doesn't have to be that way. It could be this way. We'll get the same answer either way, but I'm placing them in that order. Plane's velocity, well, I'll call this vector v for the velocity of the plane. And we'll call that airspeed later. We'll talk about that more later. And this is the wind's velocity. So I'll call this vector w. And what we're looking for is the resultant of these 2 vectors. So we're looking for the vector that's created when the plane's velocity is affected by the wind's velocity. So what we're going to get is this vector right here. This is vector v plus w. I'll call this vector r for the resultant vector. So we're looking for what is the resultant velocity of the plane. So we're looking for this vector. And remember, velocity is a vector. It has a magnitude and a direction. So we need to figure out not only what is the magnitude of this side, but we also have to figure out what is the direction that this is going in. So I'm also going to label an angle in here because I'm going to want that angle as well. So let's start by finding the magnitude of this vector. So magnitude. So to find the magnitude of this side, well, hopefully you notice that this is a right angle triangle. So we could just use SOHCAHTOA to find the magnitude of this. So if I want the length of this side, so magnitude of vector r squared equals the magnitude of vector v squared plus the magnitude of vector w squared. So 300 squared plus 100 squared. And then we can just evaluate this. We can do 300 squared plus 100 squared, and then square root that answer to find the magnitude of the resultant. Square root this answer, and we have the magnitude of our resultant is 316.2, about. So the magnitude of the resultant is, I should use about notation, is approximately, was it 316.2? 316.2 kilometers an hour. So that's the resultant speed of the plane when it's been affected by the wind. But we also need the direction. So that was magnitude, and now we need the direction. So when describing direction, remember there's lots of different ways to describe direction. We could do a true bearing, and a true bearing would be the angle clockwise from a north line, or we could do a quadrant bearing, which we could say south and then how many degrees towards east. And I think that would be easiest because this angle would give us the quadrant bearing. And we can find that angle, since we have a right triangle, by using SOHCAHTOA. So now let's find the direction. So we found the magnitude. Now let's find the direction of the resultant. So here's our reference angle. We know the opposite side, we know the adjacent side, so I could use a tan ratio. So tan of the angle is equal to the opposite side, which had a magnitude of 100, over the adjacent side, which had a magnitude of 300. And then to get the angle, when we know the given ratio, we use the inverse tan of that ratio, and we'll get the angle. So on your calculator, do inverse tan of 100 over 300. And make sure your calculator is in degrees. So we're going to work in degrees in this unit. So in degrees, it's 18.4 degrees. So the angle is about 18.4 degrees. So our final answer, we could say the resultant velocity is 316.2 kilometers per hour at a quadrant bearing of south 18.4 degrees east. So this would be the final answer to the question where it asked us for the velocity of the resultant. Okay, we have one example left. Before we do that last example, any questions? Is this making sense to you guys? Give me some indication if you need me to explain anything differently. I'll set up this last question for you all. You think if you have any questions, just write them in the chat if you have any. Okay, this is our last example. So example 6, in an orienteering race, you walk 100 meters due east, and then you walk north 70 degrees east for 60 meters. How far are you from your starting position and at what bearing? So let's just show what we know so far. So it says you walk 100 meters due east. So that would look like this. And then it says you walk north 70 degrees east for 60 meters. So this would be north, but it says then we move 70 degrees towards east. I'll just approximate that. something like that. And let me put an invisible north line in here so I can label what angle I know so far. Right, here's a north line, and it said that this vector here was at a direction of north 70 degrees east. That means that angle in there is 70. This angle here would be 90. And it says, how far are you from your starting position and at what bearing? So basically it's saying we started here, we went this way, and then we went up. So this is our resultant. We want to figure out the length of that, right? That would tell us how far we are from where we started. And we also want to figure out what direction is that vector going in. So I'll call, just to name these vectors, let's call this vector A, this vector B, and I know the magnitude of vector A is 100 meters, and the magnitude of vector B is 60 meters. And what we're looking for is the length and direction of this resultant vector, right? A resultant goes from the tail of where we started to the tip of where we finished if those two vectors are placed tip to tail. So this is vector A plus B. And we're interested in what is the length and direction of that line. Well, we can find the length of this line using cosine law again, because we have two sides and the angle contained by those two sides, right? 90 plus 70, that's 160. So I can figure out the magnitude, right? For these questions, we're always going to have two parts, the magnitude and the direction, because every vector has those two properties. So the magnitude of vector A plus B squared equals the magnitude of this one squared plus the magnitude of the other one squared minus 2 times 100 times 60 times cosine of the contained angle 160. And then let's evaluate this on the calculator and we'll get an approximate value. Just don't forget that what we get on the right side of the equation is what the magnitude of the resultant squared is. So we'll have to square root that answer. And we'll get an approximate value, right? We're not going to be able to get an exact value for cos of 160 because the reference angle is 20, but we'll be able to get an approximate answer from the calculator. So 100 squared plus 60 squared minus 2 times 100 times 60 cos 160. And this will give us an approximate answer that has to be square rooted. So second square root of that answer, I get 157.7. So it's approximately 157.7 meters from where they started. So the magnitude of this is 157.7. So I now know all three sides of this triangle. So I could find any angle in this triangle I want. And when I describe the direction of this, like I said, we could do a quadrant bearing or a true bearing. I'm just going to draw an invisible north line here as well, just because when I describe the direction of it, I could describe it as a quadrant bearing by saying north and then how many degrees towards east. And I'll call that beta. And I'm calling that beta because first, before I can figure out beta, I'd have to figure out this angle in here, angle theta, because I know that these two angles would be complementary. They would add to 90. So I'll start by finding angle theta using cosine law. So direction. And this is the last thing we're going to do. So direction. We want to find angle theta. So that's this angle here. So cosine law would be cos theta equals, and then we do the side opposite from that angle first. So 60 squared minus the squares of the other two sides all over negative 2 times that side times that side. I'll write that a little more clearly for you. So that's the setup of cosine law. We'll evaluate this, and then we'll do inverse cos of that ratio to get the angle. So it was 60 squared minus 100 squared minus 157.7 squared divided by negative 2 times 100 times 157.7. So this is the cosine ratio, and then we want the angle, so we do inverse cos of that answer. Whoops. Inverse cos of the answer, and it's 7.5 degrees, approximately. So that angle is about 7.5 degrees. So let me just show you what we have found. We have found that this angle right here is 7.5 degrees. But we're interested in this angle here. Well, I know those two angles add to 90. Therefore, beta equals 90 minus 7.5. So it's 82.5 degrees. So when describing the direction, I could say north, 82.5 degrees east. So final answer, the resultant is 157.7 meters at a quadrant bearing of 82.5, of north 82.5 degrees towards east. So that's the last example for adding vectors. Make sure you try the practice questions that go with this. This is a lot of new stuff. I mean, if you've taken physics before, you might be familiar with some of these properties. Yeah, just make sure you try the practice questions. We'll do a class session reviewing lesson 1 and 2 tomorrow on Zoom. So make sure you've tried the practice questions so that we can go over any questions you guys have with them there. Anything else before I end the stream? Remember, future lessons, anytime you guys are having questions, just type your questions in the chat. I'll make sure I see them and answer them just as we would in a normal lesson. All right, I'll wait just a few seconds. If nothing else, I'll end the stream. And make sure you guys all have a good day.